today we are looking at Le Chateliers principle, and we're going to basically explain what the Chateliers principle is, how that affects reversible reactions, and be able to predict how Le Chateliers principle will affect a reaction based on whether we change temperature, pressure, or concentration. So, firstly, what is Le Chateliers principle? Essentially, if you have a reversible reaction, you will have your reactants being made into your products and your products being made back into your reactants. At some point, equilibrium will be reached where the number of reactants and the number of products being formed is the same. That would be in a closed system. Now, if we have an open system, we will be able to change the conditions of the reaction. So we could change the temperature, we could change the pressure, or we could change the amount of reactants or the amount of products. Any change that we do is going to shift the position of equilibrium. And what that means is if we shift it to the left, then we make more of our reactants. And if we shift it to the right, we make more products. The Chateliers principle can help us predict how a specific change will affect that shift, and so we can determine if we're making more reactants or if we're making more products. Now, there's three things that we can change. We can change the pressure, the concentration, and we can change the temperature. Now, there is a little video that's attached to this presentation, which I will put as a link on EduLink. It's just a little song, because who doesn't like a science song, about the Chateliers principle, so you can watch that if you want. So let's have a look at a change of concentration. So here I've got two reactants, A plus B, being made into two products, C and D, and this is a reversible reaction, okay? Now this has reached an equilibrium, so I've got the same number of, the same amount of reactant making the same amount of product and vice versa. If I suddenly increase the amount of A, so I put more of A into my system, I am going to shift the equilibrium. If I've got more A, then I can make more C and D. So my position of equilibrium is going to shift to the right in order to make more product. So if I increase a reactant, then I can therefore make more product. So my equilibrium here shifts to the right. Okay, so if you increase the concentration of A, the equilibrium will move to the right. So the system is trying to counteract that change. So it's found a nice happy medium, but you've upset that by adding in a load more reactant. So it's gone, oh, well, if you're going to add more reactant, I need to make more product in order to balance myself out again. Okay, so that's really just all that's happening. So if I decrease the amount of A, if I decrease my amount of reactant, then again, I have upset the balance, and the system is going to try and get my amount of reactant back up again. And in order to get the amount of reactant back up again, I need to turn my products back into my reactants. So my equilibrium this time is going to shift over to the left. So rather than having that nice happy medium, my products here are going to keep going back into reactants until a new equilibrium is reached. So equilibrium will move to the left. Now, in industry, if I was actually using a reversible reaction to make a specific product, I would be removing that product because I'd want to take it and sell it or do something with it in another industrial process. So let's say that C was my useful product being made, D might be a waste product, but I'd start removing C as soon as it was made. What do you think would happen? Well, by removing C, I'm decreasing my product. So if I'm decreasing my product, the system is going to counteract that by trying to make more product, so my equilibrium is going to shift to the right so that more product is being made. So that is everything that you need to know for changing concentration. So if you increase your reactants, equilibrium shifts to the right to therefore increase the products. If I decrease my reactants, equilibrium shifts to the left to try and increase the the reactants again. And if I remove a product, then equilibrium will shift to the right to make more of that product. Okay. So pressure. Now this only really applies in reactions that are gases. So here I've got A plus 2B goes to C plus D, and they are all gases in this reaction. Now, if I increase the pressure, according to the Chateliers principle, the system will want to move so that the pressure goes back down. So anything that I do to the system will react by doing the opposite thing, to try and go back to that equilibrium. So increasing the pressure, the system wants to put the pressure back down. In order to do that, it's going to favour the side that's producing the fewer molecules. If you've got more molecules in a container, you'll have a higher pressure. So if you can produce less molecules, then your pressure is going to go down. So let's have a look at an example. So this is a real life example here. So we've got 2NO2, which is gas, and that is a reversible reaction to make N2O4, which is also a gas. Now here I've got 2 moles of gas, and here I've got 1 mole of gas. So in this reaction, 2 moles of a gas makes 1 mole of a gas. So which side has the least moles? It would be this side. Okay, this side has the least number of moles. So if I increased the pressure of this system, the equilibrium will shift towards the side with the least molecules, which would be this side. So I would therefore make more of my N2O4. Okay, so we've got colours in this, which is quite nice. So I'd actually be able to see that happening. So I would have a brown gas making a colourless gas. So it would be shifting to the right, and I would produce more of my colourless gas. So have a look at this example and see what you can think. I've got A plus 2B in a reverse reaction to make C plus D. If I increase the pressure, where will the equilibrium shift to? Which side has the fewest molecules? It would be this side, okay, because we've got 1, 2 molecules altogether, 1, 2, 3 molecules altogether. So the equilibrium will shift to the right, to the side with the fewer molecules. So if I decreased the pressure and the pressure went down, the system would want to counteract that by increasing the pressure back up. So in this case, if I decrease the overall pressure, it would shift to the side with more molecules, because more molecules means more pressure, and so it will shift to the left. I would make more of my reactants because there are more molecules on this side. Okay, so that is pressure. What about if I have the same molecules on each side? What do you think would happen then? Well, if I had the same number of molecules on each side, then nothing would happen. Okay, if I increase the pressure, then nothing I would be able to do in shifting the equilibrium would change that pressure. Okay, so it wouldn't have an effect. The last one is a change in temperature. Okay, and in this case, we need to know which reaction is exothermic and which one is endothermic. So here it's saying that the forward reaction is exothermic. Okay, so it releases heat, which means the backward reaction must be endothermic. Okay, so if I increase and decrease the temperature, have a little think, what do you think would happen? Remember, whatever happens to the system, it tries to counteract that change. So if I made the system hotter, how would the system react to try and bring the temperature back down? Well, according to Chateliers, as we know, the position of equilibrium needs to change to bring that temperature back down again. So let's say 300 degrees C was our equilibrium, and we increased the temperature to 500 degrees C. How would that cool itself down again? Well, to cool it down, we need to favour the reaction that has less heat, that is absorbing the heat, because we need to take that heat somewhere. So if you remember, our forward reaction is exothermic, our backward reaction is endothermic. So if I increase the temperature, in this reaction, the backward reaction will be favoured because this is the endothermic reaction. Here we are going to absorb heat. So the equilibrium will shift to the left, favouring production of my reactants, because that is where it's going to cool itself back down again. And we can apply that to the same example that we had earlier. So in this case, again, if we're favouring the endothermic reaction, we're going to make more of our brown gas and less of our colourless gas. If I decrease the temperature, so if I made it colder, how would this reaction counteract that? It would try and make it hotter. And the best way it's going to be able to make it hotter is by favouring the exothermic reaction, because the exothermic reaction produces heat, releases heat. So my equilibrium is going to shift to the right, where we have got more heat being released, and therefore it's going to bring the temperature back up to 500 degrees, if that was what our equilibrium was. Okay, so this is just a little summary of temperature. So if you increase the temperature in a system, then the endothermic reaction will be favoured. So it's not always the backward reaction. It may be that the backward reaction is exothermic and the forward reaction is endothermic. Okay, but whichever one is endothermic, that one will be favoured if I increase the temperature. Whichever one is exothermic, that one will be favoured if I decrease the temperature. Okay, so they're the key things that you really need to remember. Okay, you don't have to give any quantitative answers in an exam for this, so you don't need to know how much of a product is going to be made depending on the temperature changes. You just have to say which way the equilibrium will shift and whether you're going to make more products or more reactants. Catalysts. So we know that catalysts affect the rate of reaction. However, they do not change the position of equilibrium. Okay, so using a catalyst doesn't shift the equilibrium one way or the other, but it does increase the rate of attainment of equilibrium. So it's speeding up both the forward and the reverse reactions so that that equilibrium is attained and met a lot quicker. Okay, so catalysts do not change our position of equilibrium, they just increase how quickly it takes to get to equilibrium. And that's all. Okay, so the three main things to remember is we've got concentration, you've got pressure, and you've got temperature. In concentration, if you increase reactants equals equilibrium, EQ shifts to the right equals more products. If I decrease reactants, my equilibrium shifts left to equal more reactants, and vice versa if it's products. So if I increase products, then it will shift to the left to make more reactants. If I decrease products, it will shift to the right to make more products. Pressure is in gases. More molecules equals higher pressure. So an increase in pressure favours side with less molecules, so that pressure goes down. A decrease in pressure favours the side with more molecules to bring that pressure back up. And lastly, temperature. So an increase in temperature favours the endothermic reaction to bring the temperature back down, and a decrease in temperature favours the exothermic reaction to bring that temperature back up. Okay, so what I mean by favours is it will shift the equilibrium towards that reaction. Okay, so you just need to know which side is endothermic and which side is exothermic, so that you know which way the reaction is going to go. And that is everything that you need about altering conditions and the Chateliers principle.